So, hello everybody. I'm going to give a short talk about the genetic basis of PMS. So, as you all probably know, Phelan-McDermid syndrome is caused by either... You hear me? Yes. Okay, it's caused by deletion or mutation of the CHAM3 gene, which is located on chromosome 22q1333 at the end of the chromosome. The syndrome is characterized by intellectual disability, delayed or absent speech, autism spectrum disorder, and hypotonia. There is a similar frequency of the syndrome in males and females. The prevalence is unknown, although we know by studying children with either autism or intellectual disability that about 1% of these patients have PMS. So this would make PMS one of the most common causes of intellectual disability and autism spectrum disorders. PMS is certainly underdiagnosed, although it is considered a rare disorder. We know for sure that there are many patients out there that have PMS that have not been diagnosed. And especially there are patients with CHAM3 mutations that have not been diagnosed because sequencing of CHAM3 is something that is just being started to be made recently. So it's not as widespread as microarrays, so many of these kids still have not been diagnosed. The presentation of Phelan-McDermid syndrome is what we call non-specific, meaning that it's shared by many other genetic syndromes: intellectual disability, global developmental delay, language delay, autism spectrum disorders are manifestations that you can find in many, many other disorders. So it's not possible to diagnose PMS clinically. You have to make a molecular diagnosis. And how do you do this molecular diagnosis? There are two types of genetic defects that can cause PMS, either deletions, big deletions, and these can be diagnosed with karyotype, but only if they are very, very big, or other techniques that are called FISH, MLPA. But the best technique is microarray. It's the most recent one, and it's the only one that will tell us which is the extent of the deletion. So to diagnose deletions, every patient should have a microarray. But we will see afterwards that after you get the diagnosis with the microarray and you know that your son has a deletion, there are other tests that need to be done. And to diagnose CHAM3 mutations, you need to do a test that is called sequencing. That could be targeted sequencing, gene panel sequencing, or whole exome sequencing. We'll come afterwards to that. So just a reminder, in every cell of our bodies, we have 23 pairs of chromosomes. And one of these pairs is pair 22. It's one of the tiny ones. You can see it there with the red square. And the defect of PMS is one of these chromosomes 22 affecting the CHAM3 gene. Okay. So as I said, there are two main types of genetic defects. The first one, the most common one among the patients, your children here, is chromosomal abnormalities in 22q1333 region. So these chromosomal abnormalities could be just a deletion in the terminal part of the chromosome. And if it's the deletion by itself, it's called a simple terminal deletion. But it could also be a deletion that is associated with other chromosomal abnormalities, for example, a translocation in which two chromosomes exchange their tips. So it's going to be a deletion in chromosome 22, and that's why the kid has PMS. But there's going to be a duplication in the tip of another chromosome. Other kids can have a deletion, but associated with a ring chromosome, a chromosome that's in the shape of a ring. So when you are told with an array that your child has a deletion, you need to answer this question. Does my child have a simple terminal deletion, meaning it's an isolated deletion, or he has a translocate, or he has a deletion because he has a translocation, or he has a deletion because he has a ring chromosome? In order to answer these questions, after the array, you need to have FISH study or karyotype to see the ring chromosome. With an array, you cannot tell whether the child has a translocation or a ring chromosome, so you need other tests. And the other type of abnormality that can cause PMS, as I mentioned, is the sequence mutations. A sequence mutation is just a change in one or a few letters in the sequence of the CHAM3 gene. And this change can be a deletion, so one letter is missing, or it could be an insertion of an additional letter, or just a substitution. So in the first case, we have defects that are really very big, and there are thousands or even millions of letters, what we call letters that are nucleotides, what form the DNA, that are affected. Whereas in the second type, in the sequence mutations, there are only one or a few letters that have been changed. In both cases, whether it's the big deletion or the small one, the chunk 3 is affected, and the protein is going to be either not produced or it's going to be defective, and the result is PMS. The first type of genetic defect, the big deletions, are diagnosed, as I said, with microarray, but they need to be followed with karyotype or FISH to look for another abnormality. And the mutations are diagnosed with sequencing. So this figure represents chromosome 22. You see the long arm of chromosome 22, which is called the Q arm. And the end of chromosome 22 is where the deletions of PMS take place. The deletions have very variable sizes. You see here, each horizontal line is a deletion. There are big deletions that can be over 9 megabases, and there can be very tiny deletions that only include the gene chunk 3. The only thing that these kids have in common is that they all have a deletion of chunk 3, okay? Some have a deletion of many other genes, but what we know is that chunk 3 is the main contributor to the PMS phenotype. So, as I said, there can be simple terminal deletions, or the deletion can be associated with an unbalanced rearrangement. These are the translocations I mentioned. The ring chromosome, or another abnormality that is called an inversion. Okay? And some of the deletions can be not terminal, meaning that they remove the tip of the chromosome, but they are interstitial, meaning the tip of the chromosome is there. It's just a little bit of, you can see in that drawing, a little bit of the chromosome, not the terminal part that was deleted. Both types are found in PMS, but in both cases, chunk 3 has to be implicated by the deletion. 80% of the genetic defects in PMS are de novo, meaning they appeared spontaneously in the child and they are not inherited from either parent. But in 20%, so 1 in 5 cases, the kid has PMS because one of the parents was a carrier of a balanced abnormality. Balance means that the parent has a chromosomal abnormality, but it's balanced, meaning there is no genetic loss or gain of material. So that's why usually in the vast majority of cases the parents are normal, they are not affected, because they didn't lose any genetic material. Their chunk 3 is intact. But because they have this genetic abnormality, which can be an inversion or a translocation that is balanced, okay? When they transmit it to the kid, it can become unbalanced, and then the kid will have PMS. So in these cases, you understand that it's very important to know if the parent is a carrier of an abnormality, because these parents have a hugely increased risk of having a second affected child, okay? And even other family members, for example, the brothers and sisters or cousins of the parents, could be carrying a balanced abnormality that can become unbalanced in the kid, and they are at risk of having these affected children. So it's always important when you get a PMS diagnosis to answer if the parents are affected, and if not affected, they won't be affected. I mean, if the parents are carriers of a balanced abnormality, and to search for this balanced abnormality, what the parents need to have is a FISH test. Okay? If you get an array, you're not going to have a deletion. So an array is not very useful for the parents. What we need to know is if they have a balanced abnormality. This we need to see with a FISH study. Okay, so this slide shows the same thing. Deletions, every red line is a deletion. Deletions of varying sizes, very big, up to 9 megabases, very small, including only chunk 3. But we see that all patients with Phelan-McDermid syndrome have developmental delay and have delayed or absent speech of varying degrees. And this suggests that one gene explains these core features, and this gene is chunk 3. I mentioned before the interstitial deletions, and these black lines represent interstitial deletions that have been reported in patients with PMS. And as you can see, these deletions, they don't extend to the end of the chromosome, and they only affect chunk 3 or another gene, but very few genes. So the number of genes included in the deletions of PMS can vary from patient to patient. As you all know, there are patients that have very big deletions, have many genes that have been lost, and others have small deletions. So for example, a patient with a 9 megabase deletion is going to have a loss of all the genes that are represented in this drawing. So all the little blue things that you see are genes with their names, and these genes code for proteins. So this patient with the largest deletion reported in PMS will have lost all these genes, but you see that at the end on the right side, it's chunk 3 in red, which is the key gene. Okay. A patient with 4 megabase deletion is going to lose less genes, but not the less many. 1 megabase, even less genes, or 0.2 megabase is just a chunk 3 and a couple more genes. And there are even, as I said, smaller deletions with only chunk 3 involved. Chunk 3 is very important gene for the correct functioning of the nervous system. It encodes for what we call scaffolding protein that it's located in the postsynaptic density of excitatory synapses. So the synapses are the communications between the neurons in the brain, which help the communication of the neurons. And everything we do because our neurons, everything we do related to nervous functions, is possible because of the communication of the neurons. So if the neurons are not able to communicate, the language is not going to be functioning, memory, learning, and many other high functions are going to be defective. So as I said, to have a diagnosis of PMS, you need to have a deletion that involves chunk 3 or a mutation of chunk 3 gene. But there are other patients that have deletions in 22q13 that do not involve chunk 3. So for example, you see these 2 red lines here. These are deletions in patients that do not extend to the end of the chromosome. So they are very big. There are many genes that are lost. They are likely pathogenic, but they do not correspond to chunk 3. Okay? The diagnosis of chunk 3 needs to involve chunk 3. The diagnosis of PMS needs to involve chunk 3. This is another recent study that reported 8 other patients that have deletions in 22q13 that are interstitial and do not involve chunk 3. So with the other 2 that I just mentioned, there are 10 patients. And as you see, this group lined all the deletions, and they showed that there is a common deleted region represented here by the yellow line on the bottom. I don't know if you can see it. But anyway, what they say is that this does not involve chunk 3, so it's not PMS. It's another syndrome. Okay, the sizes are variable, but it could be that in the common deleted region, there is one or several genes that explain the phenotype of these kids. So we still need to learn more about this syndrome, characterize which is the critical region, what are the genes involved, but the main message is that this is another syndrome, and even though it's in the same arm of the chromosome, it's not PMS. There are syndromes in every chromosome, in every arm, all the place. In fact, there are many syndromes in chromosome 22, so it does not mean that anyone that has any kind of deletion in 22q should have PMS. These kids don't. Okay, so coming to the chunk 3 sequence mutations, there have been many mutations, as I said, pathogenic mutations describing patients with autism and intellectual disability. But what is interesting about this slide is that when you look at the frequency of these mutations, as I mentioned before, there are like about 0.7% of patients with autism that have a chunk 3 mutation, and a similar frequency in patients with intellectual disability. Okay, so this slide shows also the frequency of chunk 3 deletions in patients with ASD, and it's about 0.5 15%. So if you add 0.7 of mutations and 0.15 of deletions, you come to a global frequency of about 0.9, let's say 1%. So as I said, 1% of patients with autism have PMS. This may seem rare to you, but in fact, this makes PMS one of the most common causes of autism. And this means that every kid with autism or with intellectual disability should be tested for PMS. Okay, so as I just said, any patient with developmental delay, intellectual disability, autism, with or without associated malformations should have a DNA array to try to see what's the cause of his or her problems. A DNA array, it's also called microarray, chromosomal microarray analysis, CGH, or SNP array. All these are different types of array, but the common thing, it's a study that it's high resolution and it's going to tell us exactly what's the location of the deletion and the exact coordinates. If the array shows a deletion that includes chunk 3, the patient has a PMS diagnosis. Okay? If the array shows a deletion that does not include chunk 3, the patient does not have PMS. Okay? So we're going to focus on the ones that have PMS. As I said, there are many other questions that we need to answer after a patient has been diagnosed with PMS. What is the size of the deletion? Of course, the patient was diagnosed with an array, we're going to know the size, but there are many patients, especially among the older ones, that were diagnosed with FISH. And FISH just tell us there is a deletion in the terminal part of chromosome 22, but we don't know how big it is. And we don't know if there are deletions or duplications in other parts of the genome. That's why for the patients that have been diagnosed with FISH many years ago, because this is not the diagnostic method that is used now, for those that were only diagnosed with FISH, we advise these families to try to get an array so we can know the extent of the deletion. The other question is whether the deletion is terminal or interstitial. This really doesn't have any clinical implications. It's just, is it terminal, okay? Is it interstitial? It doesn't change anything for the clinical presentation of the patients. We would know this only if we have an array. We can know this thing. But the other questions are very clinically relevant. And this one, does the patient have a simple deletion or is it associated with a chromosomal rearrangement such as translocation, ring, or inversion? As I said, if it is associated with a chromosomal rearrangement, and if one of the parents is a carrier of this chromosomal rearrangement, the recurrence risk is increased greatly. So this is something that we need to know. And how do we answer this question, whether it is terminal or associated with a chromosomal rearrangement? By doing FISH. Or the ring chromosome can be seen by a karyotype. You don't need FISH to see that. Another possibility is when you do the array and you see that the kid has a terminal deletion in 22q, but he or she has a duplication in the terminal part of another chromosome. Okay? Many of your kids have this, and this for sure means that the kid has a translocation, because translocations have a deletion in one chromosome and a duplication in another. These kids need absolutely to be followed up with FISH to study the translocation, which chromosomes are involved, and the parents need to be tested to see if one of them carried the translocation. Another possibility is when there is a deletion in 22q13 and there is a duplication nearby. Duplication means 3 copies. Okay, so there is loss, 1 copy, but the segment, the adjacent segment is duplicated. This also, it's seen in several families in the registry, and it usually means that there is an inversion, okay? It could be an inversion that appears in the kid de novo, but it could also be a balanced inversion in one of the parents. In this case, the parents need to be tested with FISH to clarify which is the origin of this inversion. And again, it's to be able to give genetic advice to the families and calculate the recurrence risk. Okay. I don't know if I had. Okay, and of course, the important question that needs to be asked for every kid is it de novo or inherited? And I expect that I already explained why we need to know if it's inherited to give genetic advice to the parents. So the other test, so we have a patient with developmental delay, intellectual disability, autism, with or without malformations. We do an array and it's normal. So the next thing would be to sequence chunk3. Chunk3 can be sequenced by itself. It's called targeted sequencing when we only request sequencing of this gene because we suspect very strongly that it's a defect in chunk3. But usually and more commonly, it's sequenced as part of a gene panel where they sequence many genes that can be involved in intellectual disability or autism, or it can be sequenced as a part of studies that sequence all the genes in the genome that are called whole exome sequencing or whole genome sequencing. Whatever the test, at the end, what we know is the letter-by-letter composition of chunk3. And if we identify a pathogenic chunk3 mutation, the patient has a PMS diagnosis. And I wrote pathogenic in red because determining whether a change in the sequence of chunk3 is pathogenic or not, it's not an easy thing. And not every change in chunk3 is pathogenic. And not every change in chunk3 is equal to a PMS diagnosis. So this needs to be carefully interpreted by people that are experts in this type of analysis. But after we get an abnormal result of a sequence of chunk3, there are many questions that need to be answered. One, it's what type of mutation. There are different types of mutations, so changes in the letter that are called nonsense, frame shift, splice, missense. And the first three types are more likely to be pathogenic than the fourth one. But there are missense mutations that can be pathogenic, so there are more things that need to be interpreted. We need to ask whether it's de novo or inherited, so parents always need to be tested. This helps in the interpretation whether the change is pathogenic or not. We need to look whether this specific change has been reported in the literature in PMS patients, and then it will be more likely pathogenic, or whether this variant has been reported in unaffected subjects, so it will be unlikely to be pathogenic. And if we find in a kid a variant that has never been reported before, either in patients or in controls, then we can classify it as a variant of unknown significance. And it means that we don't know what it means, and we need to wait for more evidence to say whether it's pathogenic or not. And just to finish, I wanted to show you this data from a couple of years ago of the PMS registry, where it shows the type of defects that patients in the registry have. There are 232 patients. And just to illustrate that many patients have deletions that are very big, and some have very small deletions or even chunk3 mutations. But concerning these follow-up studies that I was talking about, if you look at the patients that have unbalanced translocation, there are 6%, 9% have ring chromosomes, and 3% have deletions, duplications. In all these patients, so this is like 18% of patients, this is possible that their parents are carrying an abnormality. So especially in them, in all parents, but especially in them, it's important to study the parents to be able to give them a precise recurrence risk. And I will give another more detailed talk on the genetics of PMS, and I'm going to talk more specifically about some complications that can be associated with some of these genetic abnormalities. In particular, patients that have translocations and have abnormalities of another chromosome may have other problems that are not those of PMS but of other disorders, and so this has clinical implications. And also patients with ring chromosome are exposed to certain specific risks that the parents need to be aware of, and in particular, patients that have ring chromosomes, because they are unstable, they can lose the chromosome as life advances, and they can develop a disorder called neurofibromatosis that is associated with tumors in different regions of the central nervous system and the peripheral nervous system. So parents need to be aware of this, so it's important when your kid has a deletion to know, is it a simple deletion or is it a deletion with a ring chromosome? And if it's a ring chromosome, there are things that parents need to know about possible complications that can appear in their parents, in their children, sorry. Okay.
Bettencourt's next talk will be on Saturday morning at 9 a.m. in this room, and at 10:30 it's going to be followed by a Q&A, and the Q&A is going to be in the Caribbean 4. And why are we making you move? We're making you move because all of the sessions in here are being webcast, and we want you to feel free to ask questions, without cameras on. So please join her. I know everybody's got so many questions about genetics, and 20 minutes doesn't even begin to cover, just to even scratch the surface. And I'm sorry, I am not going to really be introducing the speakers today. If you would like to learn more about them in the program guide, we have a short biography from each one of our speakers. So what we need to do now, we've had a lot of people join us since the meeting started. If you are a facilitator, I need you to raise your hand very high and make sure that we have a facilitator at every table. Is there a table that doesn't have any, where there's somebody, everybody can put their hands down? Was there a table where somebody didn't raise their hand? Do we have an extra facilitator who can join Megan? We need one more facilitator. We need a facilitator who's... Okay, we have a few open seats at various tables. Okay, so now we're going to begin. We're going to have 20 minutes of roundtable discussion for you guys to reflect on, Dr. Bettencourt's talk, some questions that you might have, and your facilitator will keep a record of the questions and the comments that you have.
Sorry, excuse me. I'll put on my teacher voice that I used to use in my previous life. We're going to do a quick couple of polls about genetics. So that's why the Poll Everywhere app is in use. I'm going to time it so that they are done within 3 minutes. And there is a poll up and running right now.
All right, we're ready to start the panel discussion. If the tables will stop their discussion, we have our panel of experts up here at the front. So we have, maybe we've gotten some notes of what was discussed at the tables and things that are concerning of parents and children with the different age groups. So first I want to introduce our panel of experts. You've already met Catalina. Next to Catalina is Joe Buxbaum, then John Bernstein, and I'm Katie Phelan. And I have to start by telling you about our agreement to disagree between Catalina, Joe, and I, because they insist that SHANK3 has to be deleted to have Phelan-McDermid syndrome, and I say it's a deletion of 22q13, and I don't care if SHANK3 is there or not. It's Phelan-McDermid syndrome, even in interstitial deletion. So that's my definition, because I think that you can have Phelan-McDermid syndrome even if SHANK3 is physically present, that maybe there's some other modulator that makes it expressed or not. And you heard Catalina's, and we disagree every 2 years we go through this. And so, that's life. Someday, one of us will be right, one of us will be wrong, or we'll all be right or whatever. So I don't want anybody to be upset about the disagreement, but we agree to disagree, right? So I was sitting at the table with the old folks back there. I felt I belonged there. And the main concern they had was they didn't understand their genetic reports, that they were given these reports and not given an explanation. And I think, Catalina, you did a good job of what testing should be done, but in somebody that has a duplication and a deletion of chromosome 22, could you go over again what that might mean and what the parents of a child who's deletion and duplication of 22q, yes.
So in those cases, and we have several in the registry, it's very possible that it's an inversion, and it's called an inverted, duplicated, deleted chromosome, dup-del, and it can occur in many different chromosomes, including chromosome 22. And this is something, let's say, relatively new, that people realize that in these cases, when there was a deletion and a duplication, there was an inversion. Inversion means that the piece of the DNA, instead of being in this direction, it switches like this and it becomes an inversion. But anyway, it's this inversion that facilitates the occurrence of the duplication and the deletion. And what's important about this is that these inversions can be present in the parents in a balanced form, meaning the parent would have the inversion with no loss or gain of material. And when they have a child, they are a very high increased risk of having another child with a deletion or a duplication. So this is why I always tell parents, please go test yourselves. Even if you don't want to have other children, you need to be aware that these type of balanced abnormalities can be present in you, but can come from your mother, your father, your grandmother even. So you can share with brothers, sisters, cousins, and they too could be at increased risk of having an affected child. And if you're the first one in the family that has an affected child, I think you have the obligation to get all the genetic testing that is required. So you clarify the situation, whether it appeared de novo in the child or you carry some kind of abnormality that could be shared with other family members. We know families here in the foundation where several generations, several nuclear families are affected by PMS because they all share a balanced abnormality. It could be a translocation or an inversion. So it's very important for the parents to get tested. As I said, with FISH, an array would not detect an inversion or a balanced translocation. It needs to be with FISH to clarify this.
Thank you. Joe, did you see anything at your table that was of concern? John, were you at a table? Was there any concerns?
At our table, there were not especially concerns, but there was interesting discussion about how testing has changed over time, and families were wondering if they should be retested and what the incremental yield of that may or may not be. That was a question. I think it's hard to make a generalization. In general, if the providers and the geneticist or genetic counselor that families work with were confident in assigning the clinical diagnosis, it's unlikely that the diagnosis would categorically change. But we do learn over time new information about the subtleties of what may be more or less likely based on the size of the deletion, for example.
And so research that's being conducted, how is size of deletion important to the research that you're conducting, Joe?
So, as you just heard, in terms of what's called genotype-phenotype correlation, there'll be a panel on this on Friday. In other words, what other genes are implicated and what phenotypes do they bring to the table? Right now there's not much known. There's clearly some bigger deletions that, you heard earlier today, and we saw also 2 years ago from Catalina's presentations that, renal abnormalities are much more likely to be only in the big deletions and not in small ones. So there are certainly things that are going to track outside of SHANK3, but we're just kind of in early days there. But it is quite remarkable from my perspective that how much of the phenotype is explained what you see just with the SHANK3 mutation. And that these, even a very large deletion may not look that different from just a point mutation. So SHANK3 is really kind of driving the show there, so to speak. Obviously, the more we know about other loci that impact SHANK3, the better we can kind of think about interventions and so on. And I think maybe this is a good opportunity to talk a little bit about the Resilience Project, which there'll be a poster on tomorrow. I think 5 a.m. is the posters. I'm not exactly sure.
8 a.m.
Oh, I was close. So, Sinai and Sage, which is a kind of bioinformatics company, a startup, no longer a startup, but been around for some time, biotech, have had this concept of the Resilience Project for quite a few years, and it's just, first major publication came out a few weeks ago. And the question behind the Resilience Project, also called the Superheroes Project, is that, there are going to be people out there with mutations that we know to be terribly damaging for some system, and yet those people will have little or no phenotype, right? And so the idea is that perhaps those people have a modifier locus. They have another genetic change that is protective, right? So in autism, we're doing this around looking at what protects girls from autism, and Allison Singer, who's sitting right there, is a major sponsor of that program. In Phelan-McDermid syndrome, we'd like to take a similar approach to actually understand, are there genes outside of SHANK3? It's one thing to see which genes make things worse, but it's far more perhaps informative, or maybe over time, which genes are actually protective. Okay? And so Sinai really has a major investment in resilience. The paper that just came out was really a proof of principle. They looked at hundreds of thousands of individuals for any of a series of very severe, rare, early development genetic mutations, and they found a small number of individuals in this huge study that actually were protected. They had the bad mutation, like the cystic fibrosis, major mutations, and they had no phenotype. So that was proof of principle. There's another study that's about to come out pretty soon from the kind of the larger group, which is I turned on my phone because I thought we were getting the text about the questions, but I'm going to turn it off now because. So one of a fairly important, I think, a very important study is going to come out very soon, showing that for Alzheimer's disease, we've now the group. I'm only associated with Phelan-McDermid syndrome, but the group now has a protective factor, a very promising protective factor for Alzheimer's disease. So people who should have had Alzheimer's disease but don't. Okay, and there appears to be a rare mutation in a gene called Caspase-7 that actually protects them against Alzheimer's disease. And so suddenly there's a drug target, right? Suddenly you can say, well, hey, if I can inactivate that enzyme in individuals at risk for Alzheimer's, maybe they'll have less chance of getting Alzheimer's disease. So that's the concept of resilience or superheroes, right? It's much harder to do. The reason the proof of principle in this first study in Alzheimer's disease were done the way they were done is because it's easier to do when you have huge samples. It's much harder to do with small samples. But there are ways that are emerging to actually possibly get some traction even in small samples. So what we're doing at the Seaver Center, and by the way, Geraldine, when she first heard of this initiative, she sent in, how many years ago was that? 4, 5? Yeah. When she first heard of it, she immediately emailed or wrote an application to the main Eric Schott and said, Phelan-McDermid syndrome should be part of it. So good, Eric didn't respond because. And so we are beginning to, compare and contrast individuals that are more severely affected with those that are less severely affected. And our definition, it's just for, it's arbitrary really, but use of language, things like that would be, higher functioning compared to no language, or severely delayed or very limited language would be lower functioning. And so we're trying to encourage people at all levels of functioning to participate, but particularly since we have so many fewer higher functioning so far, we'll get more higher functioning as the genetics, as we get more and more individuals with smaller mutations. But, we want people, particularly with higher functioning, to also kind of sign up. And it'll take time. It'll take, it won't be a week or a month away. It'll be a couple of years, but there's an opportunity here to try and find modifier loci. In other words, genes that are actually protective. And those might be ways of modifying the manifestations of the disease.
It is, okay. John, can you tell us about your research and how it might impact the patients with Phelan-McDermid syndrome?
So there are 2 projects I've been involved with over the years that have a relationship to Phelan-McDermid syndrome. One was many families here participated beginning in 2012 in creating the IPS cell repository, now available through the NIH, and I worked with, induced pluripotent stem cell repository. So these are cells that at the time were taken for skin and now can be taken for blood. The team is back here today to expand that resource, and it was a magical thing to me. The first time I heard of it, it's the idea that you can take cells that are not brain cells and turn them into brain cells, and then study them to see if you can influence the atypical brain cells from patients with Phelan-McDermid syndrome to behave in a more typical way. I'm sorry, can't hear in the back. And so I was involved on the clinical side of that from the beginning and got to meet many of the families here, and I'll be talking about later this afternoon how that involved, it's probably just me, that connection to this community has really led me to be interested in many other questions and help trainees at Stanford get involved and connected with the community here. At present, we've recently become a site in the Rare Diseases Clinical Research Network, looking at the natural history of Phelan-McDermid syndrome, led at Harvard and Mount Sinai, and I'm happy to be part of that, and we're providing a place on the West Coast where families who are interested in supporting and participating in that project can be involved, and that learning about the natural history of the condition and ultimately becoming a platform, I hope someday, for trying new therapies. I guess there's three things. And then this afternoon I'll be talking about a project that a graduate student of ours did, coming really, I'll tell the story in a few minutes, about what it's the value of having the resources we have, like the I2B2 resource and the registry and meetings like this, and the value of sitting at tables with families and hearing what their concerns are. I'll tell later this afternoon the story of our student Della Bro and how she got interested really from you about concerns regarding sleep in Phelan-McDermid syndrome and where that's taken us.
Thank you. I think from this group today, it's disheartening in one way to know that people don't understand their genetic reports, that they get a report and it's not clearly explained to them. But it's very enlightening or invigorating or inspiring to see that there's so many parents of older individuals who have been diagnosed within the last year, because we've always had a deficiency of adults, and now we have patients in their 30s and 40s who were diagnosed within the last year. And so when I've talked to those parents, I ask them, what made you get the diagnosis now? And it's always a different story, but I think that's a wonderful thing. And I think we really need to pay attention and get the word out again to neurologists, endocrinologists, physicians, the caretakers of those people, not to forget the adults and the older adults, that they need to diagnose these people. And that's kind of what I got from my table today. Catalina, do you want to add something about your research?
No, I just want to emphasize what you just said. When people come to the genetic consultations, it's amazing that they have to live with this disorder that changed their lives and that they understand usually so little about the diagnosis. And I think it's important for every parent, since this is the disease you have to deal with so intensely, to understand what are the issues, what is the genetic diagnosis, and what are the implications, to have a clear idea. And if this kind of talks, I realize, unfortunately, that it's not with this type of talks that we help parents really understand. Maybe the one-on-one genetic consultations or more like personalized explanations are better for them to try to better understand. And as you, I also noticed that my table, patients that have been recently diagnosed and mostly that have been diagnosed with the mutations of chunk3. As I said, these techniques, sequencing techniques, were done very little in the past, so these patients were not being diagnosed, and now we're seeing more and more patients with chunk3 mutations, so this is a great thing. And we will see with all these chunk3 mutations that we're going to see, let's say, a shift of the phenotype, because these patients with chunk3 mutations can be very severely affected, but some are not so severely affected and can have some language, can have, let's say, less severe intellectual disability. So we're going to see some changes in what we think as typical PMS.
That's true. The first cases that we diagnosed by chromosome studies, we were just, by virtue of the testing available to us, we were picking up 9 megabase deletions and the severe end of the spectrum of the disorder. And now we're picking up such a broad range of phenotypic features that, you know, it's really opened our eyes to what the Phelan-McDermid syndrome is. So it's always fun to come to the meeting and see how the patients have grown and what they have achieved. And now that we see them at different ages, it's really, it's a wonderful feeling, and I love coming to this meeting. Does anyone have anything to add to the?
So I think you'll hear more about this later. I know you will, actually, about life history. Alex will be talking about it. So, you know, because there was a bias towards, historically, because of the technology, toward finding only large deletions, and now we have the capacity, although it's not really done universally, to find even point mutations. You know, there is going to be a difference in phenotype as we get more and more individuals with different kinds of mutations, but also because much of the diagnosis is currently going on in younger individuals. It's really been hard to put together a kind of a map of how things change over time, or do they change over time? And that's, I think, going to be an emergent thing that the field will have to kind of really explore very, very aggressively, if you will. And one thing, of course, to do is to see the same person multiple times in a kind of longitudinal study, and the network that Alex, that you heard about earlier, that Alex is the lead of, in terms of Phelan-McDermid syndrome, is doing that because some of us have seen patients now, you know, 5 or 7 years ago and can bring them back in. But at the same time, a cross-sectional study where you look at, you just bring in individuals who are in their, you know, below the age of 10 to 20, 20 to 30, 30 to 40, is another way. It's not as good. It's another way, but it's a way of very quickly surveying what happens over time. And I think that, you know, if you have an older child or individual in your family who's recently diagnosed genetically, it's very important to try and sign up for some of these studies to understand, so we can begin to piece together, you know, what it looks like when you're 50, right? Or 30, or 20, or 10.
Thank you. Please thank our panel of experts, and we thank you for participating.